Okay, good morning. So we're still here in studying cross effects that emerge from the Onsager theory of non-equilibrium, near equilibrium, as a result of linear relations between forces and fluxes. Just as a reminder, in this slide we got these expressions that summarize the relation between energy flux and entropy flux and constituents flux, including current, electrical charge, flux, and these are diffusive fluxes, so they are relative to if we have a motion like in a fluid, they are relative to the barycenter of the fluid parcels. And this other slide also, which we have reviewed the last time, allowed us to write this term in the expression for the rate of entropy production in terms of independent fluxes, or actually in terms of these JIJs. These are differences between fluxes of pairs of constituents that are present in our system. And they go together, so the conjugated force to these diffusive relative fluxes are, we could call them diffusive relative forces, and they are given by the difference in the gradients of the chemical potentials of the same two kinds of particles. Notice that these, by definition, are anti-symmetric. So you change, you swap the indexes, you change the sign, of course, because it's obvious from here. And therefore, you see, here we have 1/2 of the summation over ij, and you're supposed to sum over all the i's and all the j's, and that will pick each of these elements twice. So the 1/2 will go away, and so for example, if you have just one pair, you will have J12 plus J21, and they will end up, this sum will end up being just one term, J12 times X12. You also should remember that we have to use the Gibbs-Duhem relation, which relates the gradient in pressure to the gradients in chemical potentials. For example, for a pure substance, so there's only one constituent, this also holds, and it says that the gradient in pressure is equal to the concentration of the substance times the gradient in the chemical potential at constant temperature of that substance. We will use this today in one of the examples. So here I've included up there, here there's still the full expression, but now I want to focus only on the vectorial fluxes and forces. So the fluxes of extensive properties that are of vectorial vectorial character. So we exclude the scalars, chemical reactions. We exclude the tensorial fluxes. So we exclude the dissipation function. You see here that we have many different terms. And then let's suppose we have only 3 kinds of particles in our system. That summation over the i's and j's ends up contributing only 3 of these products of forces and fluxes. Only 3 of them are non-zero and independent. So this will be the interdiffusion of particle 1 with respect to 2, of particle 1 with respect to 3, of particle 2 with respect to 3. And then we have the diffusion of electrical charge related to change in electrostatic potential, gradient in electrostatic potential. Of course, heat is in the gradient of 1 over T. And then there is also this term with the pressure, which gives you flux of particles driven by a gradient in the pressure. So we have 6 terms, 6 different extensive properties that can be transported in our system, and 6 different degrees of disequilibrium which control and drive the system back towards equilibrium. This is also related to the Chatelier-Brown principle, and as you remember, the more, see, each one of these degrees of disequilibrium is related to a condition, necessary condition for mutual equilibrium. So if you have no gradient in temperature, you have equality of temperature. So from that point of view, you're okay for equilibrium. But that's not the only condition. You also need no gradient in pressure. That's pressure equality, if the systems can exchange volume. This is part of the chemical potential, but it's the electrostatics. So you have you're at equilibrium, at least from that point of view, from the electrostatics, if you have no gradient in the electrostatic potential. And here also you have the equality of chemical potentials of the various pairs. If they are all equal to 0, then we are at equilibrium. The more you have of them that are different from 0, the farther you are from equilibrium, the more degree they add up to the degrees of equilibrium, and therefore, like Le Chatelier-Brown says, your system will have a stronger tendency to return to equilibrium. And the way the system returns to equilibrium is described by this big matrix. In fact, I didn't put the tensor signs, but these are each of them is a tensor, because the most general relation between a vector and another vector is through, even if linear, it's through a tensor. So you see how rich the variety of phenomena that we can encounter and that we can model is. So, of course, if you want to include all of them, you need computer program to do it. This is done in simulations, but even though nowadays we have computers and we have software that are very they're able to model very complex phenomena in fluids, and not only fluids, because of course I'm talking of fluids, but also in solids that we have the same ideas. Very seldom they are implemented to include all these off-diagonal terms. Most of the times, you just keep the diagonal ones. For example, here I've already sort of shaded out these off-diagonal ones, because most of the times you assume that each pair, so the relative flux of pair 1, 2 is driven by the relative difference in gradient of chemical potentials of that pair, and not the other ones. But these are possible cross effects, and these possible cross effects may result in, for example, the possibility that concentration gradients, you have two different, so you could have a flow upward the concentration gradient of one constituent driven by the flow downward of two other constituents. And part of it could be captured by these, but I think that if you want a most general description of that, you would need to include also these off-diagonal terms. Okay, now we have already done thermoelectric effects, and from this point of view, the thermoelectric effects cover these degrees of disequilibrium. So a material in which you have a gradient in temperature and a gradient in electrostatic field. And so our system becomes just 2 by 2, two quantities, extensive quantities transported, and 2 degrees of disequilibrium. And since we are at it, I think I should, there was something wrong in the view graphs that in the slide where I did this calculation last time, so I corrected it now because I was using the wrong expression for the work triple work. So here I've taken a slightly different approach to correct that. First of all, I write what the reversible work is, and you remember in the situation like we have done when we did the heat transfer. So we had here this is x, here is t, and here is t plus dt, and then we put in an engine that receives a heat flux, and like a Carnot engine with the Carnot efficiency, because it's a reversible engine, produces a W, let's call it TH for thermal, reversible, which is given by that minus Q gradient in T over T. Now, here we also have a gradient in the electrostatic potential. So we can use that by extracting with an electric motor, for example, some work also this way, and that will add an electrical work reversible, which is given by, since the effect that the gradient in the electrostatic potential is driven by the Seebeck effect. This is given by minus I times the gradient in phi, and that's minus I times epsilon gradient in T. Or maybe, sorry, there is no minus here. I drive a current down from high potential to low potential, and the power of the engine is current per voltage. The power is current per voltage, and so there is no I here. The minus sign comes from the relation for the Seebeck effect. So that's what I've done here. And next, I say, well, the actual, if I put my thermoelectric generator, and it does have some entropy produced by irreversibility, and that entropy produced by irreversibility is given by the Fourier term and the Joule effect term. Of course, the actual work of the generator will be less, will be the reversible minus T times sigma. And since I was there, I just decided to keep also all the tensors that I know complicates the story, but since I haven't seen it done anywhere, not that I looked everywhere, but so I said, well, why not working it out? And I hope I did the right thing. So using that expression and substituting the thermoelectric electric relations, these ones, you find an expression for the actual electrical work. You can maximize it, so you find at which current density it has the maximum power. So maximum power doesn't mean that the engine is reversible. It's a particular point of operation of the engine and or generator. And so if you compute this current, if you substitute this maximum current density at maximum power into the expression for the work, you get this expression here, where there begins to appear, now I highlight this parameter Z, which for an isotropic material takes this form, and it's what is called the parameter of merit, the figure of merit for the thermoelectric material. And there are some materials that have that parameter of the order of 1, but there are also some nanostructured materials that go well above 1, maybe I think even 2 or even 3. And this is why the fact that you can achieve, and that nowadays you are actually engineering materials by layering, exactly like we did for the non-isotropic heat transfer example. Here you can cook up layered materials that have properties, alternate properties with high conductivity or a low high Seebeck coefficient and low conductivity, thermal conductivity. And depending on how you structure them, you may obtain good aspects of this tensor, which of course relates to the properties of how much it, in the if the directions come in, see the gradient in temperature dotted into the tensor means that the directions are important, the relative direction of your material and the direction in which you put the gradient. Okay, then once you have this, you can also substitute all the rest in all the rest and compute also the second law efficiency. Second law efficiency is the ratio between the work at maximum power and the reversible work that you could get with that current that you have at the maximum power. And this is the generalized expression for that efficiency, which for the isotropic material becomes this one. The figure of merit divided by 1 plus 2z. And if you look at this function, z and what is it? Z divided by 1 plus 2z. Well, it's a function that, of course, is 0 at 0. And then it goes up. And eventually, it could reach 1. Does it reach 1? Or does it reach 1/2? It's a good question. Yeah, it looks 1/2, yeah. Okay. All right, so this fixes that error that I made a while ago, but it's, errors are instructive and stimulating so that you try to correct them, so that's good. Here is another example somewhat similar to that one. Think of having, instead of the electrostatic potential, having the pressure. So you have two reservoirs, one at T and P, and the other at T plus dt and P plus dP. So here you could, since you have, suppose this is a fluid, well then you could use, in addition to the thermal work, you could use the difference in pressure to drive a flow through a hydraulic turbine. And the work of the hydraulic turbine is given by the difference in pressure times the volumetric flow rate, like in a pump. No? So that is sort of very analogous to the thermoelectric effect. And so with this pair of degrees of disequilibrium, oops, sorry, here, no, yeah, okay, so you treat exactly, you take those two elements that survive in the expression for the entropy production, you assume linear relations, and now the flows are heat and instead of charge, here now you have just particles. And if you divide the flow of particles by the concentration, you get a volumetric flow rate. So this is cubic meters per second per square meter flowing. So you can rewrite, because usually what we do is rewrite these expressions where we have been careful in using the entropic degrees of disequilibrium, so that we know that that's where the Onsager reciprocity applies, and so I can safely say that these coefficients LQP is equal to LPQ. Here Q stands for heat and P stands for pressure, of course. And so now at this level I can apply Onsager. But then we like to work with more familiar variables, which in this case are the volumetric flow rate, and the gradient in pressure is already there, and the gradient in temperature instead of the inverse temperature. So we introduce parameters like the thermal conductivity, or on the other diagonal element is usually written as K over nu, where nu is the viscosity, the shear viscosity of your fluid, and K is the Darcy permeability. Because if you had only this diagonal term here, this is simply Darcy law of flow in like in a capillary or in a porous medium driven by the gradient in pressure, which is what you would use, for example, to describe the flow in a porous material or a permeable membrane, like here, or in a capillary tube or in a microfluidic device or things like that. But the off-diagonal terms are also there, and they give rise to two cross phenomena that are related to one another, that sometimes go under the name of Thermo-osmotic effect or mechano-caloric effect. So the Thermo-osmotic is this one. No, I'm sorry, Thermo-osmotic is this one. You have a flow of material in the absence of gradient in pressure driven by a gradient in temperature. We could actually have this flow go, if the gradient in pressure is small but opposite to what it would drive, what the Darcy law would drive the flow, you could go against that pressure gradient by using a thermal gradient, appropriate thermal gradient. So that is one way in which you could somehow drive your material in a capillary or microfluidic device with a gradient in temperature against a gradient in pressure. And the opposite, or the the conjugated cross effect, is this one, where you would, without a gradient in temperature, you could have a gradient in pressure that drives a heat flux. But also here, you could have, if depending on the relative differences, you could have a gradient in pressure drive heat against up a temperature gradient, so in the opposite direction of what you would expect if you just had Fourier. Okay, so now let's move into the realm of diffusion of particles. So the simplest is when we have two constituents, like a pair of particles. So we have interdiffusion of one into the other. And so this is a sort of a direct law case, which you which gives rise to Fick's law of diffusion. Or also, since we're talking about a pair, it belongs to, instead of Fick, it's called the Maxwell-Stefan law of diffusion. And here is the story, actually. See, on the left-hand side here, it's just repeated all the various steps that took us to the relation I just said. So let's just look at what we have here on the right-hand side, which is the new aspect. So we assume a linear force flux law, and as we've seen in the previous, is just a direct effect. The degree of disequilibrium x12 drives a relative flux J12 through a coefficient that, yeah, on the previous slide we call it L1212. Here, just sort of drop the double 12. Okay. Usually, there are a couple of ways in which this is typically rewritten. So there is no single familiar way of rewriting this. We like to rewrite it in terms of diffusion coefficients, which are the things that we measure in the laboratory, or we measure also nowadays with Monte Carlo or molecular dynamics simulations. And so we call this L12 this way, identify, so these are the concentrations of the two constituents. And of course, they are related to one another, no, because the mole fraction is of the second species is 1 minus the mole fraction of the other one. So also between the concentrations, you have a similar relation. Because, all right. And so the other aspect is that you somewhere, yeah, here, here, you notice that you can prove that the x12 can also be written by virtue of the relation of the Gibbs-Duhem relation. Can be written also in terms of either just one gradient. X1 is just a gradient in chemical potential of substance 1. So it's this one, like -1 over T times the gradient of mu1, and that's x1. But you could also define an x2, and these are all related to x12. So by substituting and expressing these in terms of the flux of particles 1 as proportional to the gradient in chemical potential of that particle, you can rewrite it this way. And then the gradient in chemical potential of particle 1 can be related, if you do properly the various derivatives, since the chemical potential is a function of the concentration. So you remember our usual expression here for example, for an ideal mixture. For an ideal mixture, you can write this, and therefore the gradient in the chemical potential done, because here we are at temperature, fixed temperature and pressure, so this doesn't enter into the gradient, and so then you get that gradient in mu is RT times the gradient of the logarithm, so that's that's the gradient over y. And of course, since the mole fraction are related to the concentration, you can also rewrite it in terms of concentration. So that is, I mean, this expression is for the ideal. If you have a more general situation, you would have to do the partial derivative of mu with respect to n, which is written here, and that's what appears here. So if you include all these, then you have a relation between the flux of particle 1 and the concentration of particle 1 times the gradient in the mole fraction. And then you can call this group the Fick diffusion coefficient, which you see is related to the Maxwell-Stefan diffusion coefficient. And so it all depends on giving names to these diffusion coefficients. Typically, people measure Fick diffusion coefficients. Notice also that you can also define a self-diffusion case. This is done, for example, suppose you have just water in your box, but suppose that some of the oxygens, some of the water molecules, some percentage of water molecules are doped. Well, actually, they are made with isotopes of oxygen. So instead of using oxygen 16, you use oxygen 18. So you have water molecules that have an isotope for the oxygen. The isotope doesn't change the chemical properties, but that allows you to, with proper detection, to follow the diffusion of the sort of a heavy, it's not really heavy water because the heavy water is with deuterium, not with the oxygen 18, but that in this case it's a heavier water than the other one. So you can see the interdiffusion, and of course this diffusion is related to the Brownian motion, the random motion generated by collisions and the kinetic energy that the particles always have at finite temperatures. So in that case, you measure the self-diffusion of water, which is an interesting case and sub-case of this one. Now, if in addition to having gradients in concentrations, you have also gradient in temperature, this opens up to diffusion or thermodiffusion effects. And so the transport, thermophoresis means, remember, phoresis means transport. So you generate a flux of particles with a gradient in temperature, even if you don't have the driving force in the gradient of the chemical potential. So even if you don't have gradients in concentrations, just the gradient in temperature drives particles. So that is this is the written explicitly x12, which is minus 1 over t times the gradient mu1 minus mu2. we can write it also in terms, like I've said here, with the partial derivative starting from the chemical potentials. You can write it this way, in terms of the concentration. Yeah, sorry, this should be a C1 over C1, not I. I'll correct that. Yeah. Okay, so this is the setup. So that's the usual formula for the entropy production, from which you infer what are the entropic degrees of disequilibrium, which are the ones that enter in the linear force-flux relations. And so the force-flux relations are these. You therefore put in a matrix of coefficients, and the matrix has to be symmetric. So we will have that LQ12 is equal to L12Q. And we rewrite it in so-called familiar variables, or the traditional ways, so as to single out the gradients in concentrations instead of the gradients in chemical potentials. However, when you do that, your system of equation loses the apparent symmetry. So you see these off-diagonal terms are not identical. But I have used, in order to put this dt here, you see dt is called the thermodiffusive coefficient. And whereas d12 is the Fick. So this is the Fick, the diffusion coefficient is the direct effect between, so it's you drive a flow, a flux of particles, a diffusion of particles by the concentration gradient of one of them. And whereas this drives the flow of particles, the flux of particles, the diffusive flux of particles with the gradient in temperature. And you can enter these equations in many different ways. For example, if you assume no gradient in concentration, then you have the heat flux that is simply given by Fourier law. Or if you choose to work at zero gradient in temperature, the second equation gives you Fick's law. You could also consider, though, that when you work at no gradient in concentration, you don't have only the first equation, you also have the second equation. And that gives you a flux of particles driven by just the gradient in temperature. That is the Soret effect. This is the effect whereby, for example, you have dust particles in the air that collect, like you may have noticed, or you probably know, that in your house you often find dust near the cold walls. That is the Soret effect, because from the mechanistic point of view, suppose this is a dust particle, so it's a large particle with respect to the molecules of air, and let's say these are molecules of oxygen, nitrogen. And so suppose you have a gradient in temperature this way. So you get cold here, and hotter there. Okay. So the idea is simply that the particles on this side have a higher kinetic energy, and when they bounce on the particle, of course, they exchange that, they exert a force on one side that is slightly less than the one exerted by the collisions with the particles that come from the cold side, which are a bit slower. So this pushes your dust particle towards the cold. Notice also, yeah, and the opposite effect, the conjugate effect is the Dufour effect. So when I have a Fick law at no gradient in temperature, so I have a flux of particles driven by concentration, but I also have a heat flux driven by the concentration. Okay, so it's like the flux of particles that carries with it also a heat flux, and that's the Dufour effect. These effects were discovered separately, then only later they were linked by the Onsager theory of reciprocity. Also, it's interesting to note this, that for example, suppose you have suppose you have no flux of particles, so you set this equal to 0. Okay, so if you set that equal to 0, you see that there comes a relation between gradient in concentration and a gradient in temperature. So if you suppose you impose a gradient in temperature, then, and there is no way that you don't allow this flux of particles, then the gradient in temperature builds up a gradient in concentration. And that gradient in concentration has a play in the first equation up here. And it reduces the effective conductivity. So the conductivity, the thermal conductivity at no concentration is higher than the thermal conductivity at no diffusive flux. Okay. Now that simple picture that I have shown here on the blackboard is one possibility, and it's one mechanistic possibility that explains the Soret effect, or the Thermophoresis, so the transport of dust particles towards the cold side. In part, that is due to the size of the particles. And so it belongs, this nice article that summarizes thermophoretic mechanisms shows that there are many other mechanisms that drive the Soret effect, that control the Soret effect. So typically, the heavy particles like to get moved to the cold side, or the skew particles, or the large particles. But then there are also more sophisticated actions, including some double layer effects on the surface of particles that have some charge on their surface. So there is a a whole realm of possibilities with which you can use Soret effect to drive things towards the hot or towards the cold, depending on how you engineer your materials and or the properties of your materials. This is another paper that shows how you can use a gradient in temperature to move particles against friction force in a small pipe. This is the carbon nanotube in which you have water molecules, and so you manage with a gradient in temperature to win the friction forces, because one of the problems in moving stuff in small pipes is that you would need huge pressure drops if you wanted to do it with a pump, and that will the device will break because of the high pressures, whereas thermophoresis or electrophoresis are more effective and more doable. And this is also in a thermofluidic device, the idea that the gradient in temperature, so you have like a hot flow which keeps a hot side, and a cold flow which keeps a cold side, and then you have your actual device with particles in it, and you want to separate the particles, and that's what happens by Soret effect. Let's say the particles go to the cold side, and so you reach a separation in your device. Now it is also important to realize that what we have covered here is only a very minor aspect of the phenomenology that goes with diffusing particles. And so what I'm doing with these slides is I don't pretend I can describe what happens, but I want just to suggest that the variety of phenomena that needs to be discussed, if we had, let's say, another course, but also by another teacher, because I'm not prepared on this topic. But maybe the next teacher of this course will be, and so there are, for example, we talked about the Knudsen number, the relative size of the mean free path relative to the dimension of your device. So if the Knudsen number is very small, then your particles, let's say that if they make at least 100 collisions before traveling a distance of the order of magnitude of your device, which so it could be the diameter of your pipe, then we are safe, and we are you can make the continuum assumption that we have made in what we've done. But if the Knudsen number becomes larger, and you may reach the other extreme, which is the ballistic extreme, in which a particle may travel all the way from one side to the other of your device without even having a collision. So this is not dominated by collisions between particles, but it's dominated by collisions between particles and the walls of your device. Plus, there are surface effects, and so you see there is a variety of things that need to be considered. Now, thermophoresis can also is also used as a way to move particles around. This is called self-propelling particles. For example, here we have a PhD thesis and an article that talks about using a phenomenon that we have discussed, which is a spinodal decomposition, in order to move around particles. And there are two kinds of particles. This one, which has a double face, it's called Janus particles, because Janus is the god with two faces, Greek god with two faces. So this is this particle is gold-plated on one side and not on the other side. And the gold surface layer guarantees, since it has a high conductivity, guarantees a uniform temperature. And so then what they do is to shine some laser light to heat up that particle. And therefore, a temperature profile builds up. And then they find a solution. So the particle is in a solution which is non-miscible at high temperatures. So we have studied spinodal decomposition in substances that have an upper critical point. Remember, and this is the spinodal curve. This is the unstable, and this is the metastable region. Okay, so you could do that phenomenon, that thing, if you could cool down the particle, but it's easier to heat up than cool. So they found it easier to develop mixtures that work the other way around. From what I remember, also water and nicotine as a lower bound, as a lower critical point like this. I don't know exactly what substances they use here. Water and 2.6 lutidine, okay. Whatever that is. In any case, the idea is that you start, I mean, the blue mixture, which is on the surrounding the particle, is at this point. So it's fully mixed. And then, since you heat up the surface of the particle in this layer, say boundary layer around it, the temperature goes up and you enter into the unstable region. And the unstable region creates let's say the free energy, and that free energy, if properly directed, can be used to propel the particles in two ways. You need asymmetries. So for the Janus particles, the asymmetry is on the fact that you have more heating on one side than on the other, and therefore you generate a concentration gradient from this side to the other side, and that movement of particle in one direction propels the big particle in the other direction, and so you get the particle move. Or here they have still a gold-plated particle, but all around, so it's not Janus, but it's not completely spherical. So it's a non-spherical particle, and the non-spherical aspect here makes it so that the gradient in the concentration and the gradient in temperature cross. So that crossing means that these two gradients are not directed in the same. So there is a component of the gradient in in concentration that goes orthogonal to the gradient in temperature, and that will cause the movement of particles that will push your big particle, I think, downward. Okay. So you can play also. You can play. People are playing because you see this recent. This is recent work. There's a lot that people are doing using these methods. Or another way to exploit or deploy non-equilibrium is what they are called molecular motors, which essentially are nano particles that develop motion at the expense of chemical reactions. And here, for example, the particle it simply has a catalyst or an enzymatic site which catalyzes the chemical reaction, so it lowers the Arrhenius activation energy only locally here. So it promotes chemical reactions in this side of the particles. Of course, the chemical reactions change the composition. The change in composition creates a gradient in concentration, and that's how you get flux of particles. In fact, we said that the Curie symmetry principle prevents, in an isotropic medium, to couple chemical reactions which are scalar transport with vectorial transports. But on the other hand, diffusion is sometimes the limiting aspect in chemically reacting system, because it is by diffusion that particles go to the proper place and then where they're used up for reacting with the other reactants. So indirectly, diffusion processes are very important in controlling chemical reactions. So they are effectively not coupled in the way of the Onsager kind, but they are coupled overall in order to feed the chemical reactions with the reactants where they need to be. And then if you have simultaneously a diffusion, so many constituents, and also the electrostatic field, the charges play a role. They may play a role just locally, like these kind of double layers around particles that have charges inside that can move to the surface. And these effects are things that happen, for example, at electrodes in a fuel cell or an electrolytic device, or simply you have like a thermoelectric effect coupled to diffusion. So this is so electrochemical systems belong to this kind of class. And these are the kind of equations that you need to consider if you model an electrochemical system with, say, 3 different particles. And 3 different particles is very common because you may have the solvent, and you have 2 solutes, but often you have many more. And these solutes could be the ions that travel in your electrolytic solution. The typical models are done this way, with this interdiffusion taking up only the diagonal ones, and often forgetting these other more complicated or second order, maybe, cross effects. But if you are interested in doing modeling electrochemical systems, then these are the references that you should not overlook. This book, Non-Equilibrium Thermodynamics for Heterogeneous Systems by Kierstrup and Bedeau, is an excellent starting point for doing properly things the way we've done. And also for realizing that so you can compute distributions in the heat. They use the Groth and Mazur notation. So what we call the Q double prime, they call measurable heat flux. But other than that, they essentially use the same notation that we've done. And also, a very important aspect here is the interfaces at the electrodes, and so where you have you have sort of jumps from one substance to the other, and yes, you could define continuous or diffuse interface theories, which is another aspect that needs to be covered. But they do it with sharp interfaces, which is the Gibbs traditional method. But the reason why I urge you to go to their work is that they do it correctly and carefully. And in particular, also regarding this role of interfaces and the non-equilibrium thermodynamics at surfaces, there is this paper again by one of them, Dick Bedeau, in 1986, which is really wonderful, and you should study that paper if you are in this business. Now, of course, we are at the end of the course, so I'm not covering anything more of, but I want to mention that there are many other directions in which you could go in the field of thermodynamics, which is related to the general principles that we have developed, but perhaps not the detailed models. So, of course, the queen is statistical mechanics, which is behind. We've used also some of it when we did the single particle in a box. But then you have also kinetic theory to deal with rarefied gas dynamics if your Knudsen number is not very small. And in fact, to cover that the phenomenology of essentially the entire fluid mechanics redone at the known Knudsen, very small Knudsen number. People have redeveloped. There's been a couple of decades of very active work on small-scale hydrodynamics, still ongoing. Then on the side of developing the foundations, so even for continuum, we have this issue. Remember that of the local equilibrium, where we assume that we are at this state, but we're actually there. And so there is this difference in entropy that we are neglecting if you do local equilibrium, and which is not neglected in these other theories, like rational extended thermodynamics or other non-equilibrium thermodynamics theories. And there are not only papers, but books about these approaches. And you've seen that by using these, we've seen one example, the Cattaneo heat transfer equation. Well, in that same idea, you can develop, and you should develop also all the things that we've done, even including what we've done today. So there is a lot to be done also in that direction. There is also, okay, then there is quantum aspects. We talked already about that. And there is also this diffuse interface methods that, again, if you have two phases, you could consider them as sharp, like, for example, liquid and vapor. You could have, this is the density of the vapor, and this is the density of the liquid. Let's say, yeah. You could consider it sharp, but if you enlarge this region, it's actually something like this. Okay. And by assuming a fundamental relation for your states, for example, by assuming that S is not just a function of U V N, but it's also a function of the gradients in concentration. And actually, since you need a scalar, it's, you can take the square of the gradient, and you put in it as an additional variable which determines equilibrium. And now we are talking about equilibrium because that's a stable equilibrium state for equilibrium. That term there, which was present also in a paper by van der Waals, and which actually is a very nice paper. It's been translated by Rawlinson later on, and I suggest that you go and see that paper if you are studying this. Well, this theory here has been developed by Landau. It has been developed. This has now become known as Kahn and Hilliard models, or diffuse interface methods. With that thing, you can predict the exact shape of this curve at equilibrium. And actually, there is a paper, very nice paper in the Physical Review by Antonovsky that I suggest that you read if you are interested in, in that kind of development. All right. So, plus, of course, you have a list of, an infinite list of other approaches, from statistical to numerical simulations of the Boltzmann equation, approximations of the Boltzmann equation. This is a famous one, which allows you to compute the hydrodynamic quantities like heat flux, but also so the fluxes of particles, but also the like momentum and diffusive as moments of the Boltzmann distribution of equilibrium. So we're talking about models that can cover also non-equilibrium and Far-Nonequilibrium. Another approximation is one which derives the equivalent of the Navier-Stokes equations, but more complicated with more moments. Then the Fokker-Planck, stochastic equations. These are equations that have some random noise terms in it. And then you're certainly familiar with molecular dynamics, Monte Carlo, and various types of molecular dynamics, various flavors of the molecular dynamics that have been developed over the years to overcome some of the limitations. Okay, so yeah, so with this, I think I'd like to end the course, remembering that we have celebrated Carnot's 200th birthday and I also, yes, I want to remind you of the Prigogine Prize. So if you ever end up with a PhD thesis in the field of thermodynamics, all aspects of thermodynamics, from applied to experimental to very theoretical, don't forget to apply for this prize. It is done every 2 years. The next deadline is February 1st next year. And for this call, it will cover PhD defended between January 1st of last year, 2023, and December 31 of this year. It's a pretty international prize. In the last 8 editions, we had 134 candidates from 28 different countries. You can click here for all the details. And it is sponsored by a series of conferences called the Joint European Thermodynamics Conference, but it has become an international one. And the next one will be in Belgrade in Serbia next year in May or June. The date has not been decided yet. As soon as it will be out, I'll put in a link here so that you can see what it is about. All right, so I'd like to conclude, and I'd like to thank you for attending the lectures, which I dedicate to my mentors, and but also I thank you very much for the quality of your video homeworks, because they have been stimulating me for at least as a giving me some feedback that some of the messages I wanted to pass have been passed. So thank you very much.